Welcome, everyone. So let's go to the third lecture of Professor Gukov on Vertex Algebras and quantum invariants of 3D, and, 3 manifolds and 4 manifolds.
Yes, thank you. So as usual, I'll share the link in Zoom chat to the whiteboard. Feel free to follow it. It's of course posted on the website, so feel free to follow it at your own leisure. I'll also try to share the screen and again, tell me if I forget to move it accordingly. So last time we finished with various questions that naturally come from this correspondence between vertex algebras, or characters at least of vertex algebras, logarithmic ones, and this invariance of graphs. So I call them invariants because we already saw that they're invariant under so-called Kirby-Neumann moves. So today my job is to clarify some of these missing points from even the first lecture. But let me first summarize once again why, or some of the motivation why we're doing it. So at least in various cases, there was observed this conjecture. So it's observation in some cases, and of course conjecture more generally, that if you compute this object z hat, so far we did it for various graphs, so as a function of graph, and more importantly as a function of Q, then what comes out is a character of some log VOA, so it's a trace over some module, let me call it VB, Q to the L naught minus C over 24, and here VB is log VOA module. So a stronger version of the conjecture could be the following. Remember, I mentioned in the very beginning that this object z hat, in the way which we'll also see later today, actually is meant to be a graded trace of some space. So I mentioned it without too much justification, but if we take that for granted, a conjecture or stronger version of this conjecture, so stronger form, would be to postulate that this underlying space, I think I denoted H BPS because it has to do with counting of something, of 3 manifold or graph, and also labeled by this choice of B, this itself could be the module VB. I have no evidence for this a stronger form of the conjecture. In fact, checking it is, of course, extremely hard because this requires control over space. So the first version is about functions and the latter is about space, but of course it's more insightful. But I want to emphasize is that that's why even the first conjecture is interesting, because it's a stepping stone toward this bigger one, and this bigger one will be basically price of gold for topology, because in topology people are obsessed with categorification, and this is a very hot topic in recent years. In fact, this was exactly the motivation for this invariance z hat. In a theorem I stated before, I emphasized that they have integer coefficients, and always integer coefficients are supposed to be thought of as graded traces of some vector spaces. And therefore, if this bridge between vertex algebras and such invariants is developed, it will necessarily shed light on categorification. And then again, take my word for it that in topology, this is very hard, very important, and something we definitely care about. So that's the motivation. But to answer any of these questions, we, of course, have to start with more basic questions. And the ones above are basically an illustration or a stepping stone to establishing this dictionary. So of course, before we can run, we have to learn how to walk. And the question is that in fact some of you already asked once we introduced this object. So we have to ask what kind of function or object is this that had be either for a graph or, as we'll discuss today, for more generally three manifold. So answering this question will necessarily help comparing it to characters. So for instance, if we know some modular property or growth of the coefficients, then we can be more assertive about what to expect on VOA side. And this is obviously much more manageable question. So today I'll do two things. So first of all, I'll explain connection between graphs and three manifolds. So this will be, we'll start sort of in topology. This will require us, so this is the roadmap, to go to quantum groups. In order to understand or generalize story properly. And from then, so first of all, there are already many connections between quantum groups and vertex algebras that usually or generally can be packaged under the umbrella of so-called Kazhdan-Lustig correspondence. But what's interesting is that today, so that's not the connection that I'll try to emphasize in the end of this last lecture. I'll emphasize something else where by going into quantum groups, we'll have yet a different connection to logarithmic vertex algebras and their characters, something that goes by the name of fermionic forms. Of VOA characters. And this will shed light on, this will answer the previous question, namely what kind of function is this? I want to point out that it's a little counterintuitive because what we'll do, we'll take the setup that we already saw so far, and even for these graphs, as you can see, we can compute this Q series, but answering what kind of function is not obvious. I mean, how do you recognize if it's a Q hypergeometric series or one of these Ramanujan's examples or something more general? And surprisingly, generalizing this question, which will be forced on us upon topology requirements, will actually help us to answer what kind of function. And this will be a new connection that is very recent. And again, its full depth and implications are definitely not explored yet. And the connection, this last one, which will be most important, will come from another structure of combinatorial nature by the name of quivers. So they will come in at some point and will help us to make this link. So let's that's the plan for today. As you can see, it's a lot, but it's actually hopefully will be achievable, so that because explaining one thing will help the other. So there will be a couple of surprises on the way, and this way we can feed several birds with one stone. Okay, so coming back to topology, I want to start with a theorem. So that's in some sense, important theorem underlying much of what happened before. It's a theorem due to Licorice and Wallace. And I'll also add the name Kirby here for reasons which will become clear in a second. And the theorem says that every closed oriented three manifold arises or can be obtained.
Can you scroll down a little bit?
Oh, yes, thank you so much. Yes. Arises by performing an integral surgery or sometimes called Dane surgery on a knot or a link which I'll denote by K inside 3-sphere. So that's the statement. So let me unpack it and clarify a couple of things. So first of all, what is a knot? A knot is embedding of a circle in 3-dimensional space, and without loss of generality, we can take 3-dimensional Euclidean space compactified with a point that makes a 3-sphere. So link what's an example of a knot? So for example, in Rolson classification, knots are classified by number of crossings. There is only one knot with 3 crossings called trefoil knot. And it looks like this. Let me try to do this exercise in drawing. Here it is. So this is a 2-dimensional diagram which has overcrossings and undercrossings and illustrates what a 3-dimensional knot in 3-sphere looks like. So link is basically the same thing. So link is analog where you have several connected components of your domain. So you have a bunch of disjoint circles embedded into a 3-sphere. And again, if I am to give a simplest example, then perhaps Hope link is the first non-trivial case where it has 2 components and they're embedded like this and a link together. So that's a link. And in general, you have many more components that can be intrinsically knotted and so on and so forth. So so this explains what a link is or not is. What about the surgery? What's that? So a surgery is the following operation. So we start with a knot embedded in a 3-sphere. Let me just draw a single knot with 1 component for simplicity. Something like this. I'm going to draw it bigger. So that's the same picture of a trefoil, which is the only knot I really know how to draw. And our manifold embedding, it's embedded in a 3-sphere, so we want to construct a new space out of it. So what we do is we take out tubular neighborhood of this knot. So I'm trying to illustrate it in green. And reglue it back. So what it is, so what remains is when we remove, first of all, the tubular neighborhood is a so-called complement of a knot. So in this way, we represent S3 as a union of a complement and the neighborhood of a knot is S1 cross a disk. It's a topologically solid torus. And when we start with our S3, these 2 pieces are glued along a 2-dimensional torus boundary, which is common to both inside and outside of this green region, which is exactly this 2 torus. Now, the idea of Dane surgery, which in general is called P over R surgery, where P and R are relatively prime positive integers. Sorry, not necessarily positive integers, but they're usually relatively prime. Is the following: we take this same two basic pieces and construct a new manifold out of it. So it's analogous to what we had for S3, except that now it will be denoted as S3, labeled by P over R, and depends on the choice of knot. And by definition, so this is the definition of a surgery, it's those two same pieces, namely S3 minus the knot, that's the exterior of your green region, and the neighborhood of a knot, which is the solid torus, S1 cross a disk. But they're now glued via a non-trivial element phi by noting that the mapping class group of a two-dimensional torus, the group of cell diffeomorphisms which are not connected to identity, is PSL2Z or SL2Z. I'm not going to worry about the quotient by plus minus 1. And basically, all such diffeomorphisms can be, or ways of gluing these two pieces, can be represented by 2 by 2 matrices, where the most important part is what appears in the first row. These are precisely these integers P and R, and these other elements are not very important. So this defines general so-called P over R surgery on a knot or a link, and integral Dane surgery, which was used in the above theorem, is a version of this where R is equal to 1. So I'll put this definition next to our pictures. I'll say that surgery is integral if the surgery coefficient, this P over R, is integer. In other words, if R is equal to 1. Okay, so this explains the two important words in the statement of this theorem, that first of all, what knot or link is, and then secondly, what is this operation? The claim is that you can construct any three manifold you want. All three manifolds in the world can be constructed in this fashion. And constructions, sometimes different constructions or different knots and different choices of surgery coefficients give the same result, namely same three manifold. And if that's the case, they are related by Kirby moves. So that's precisely why I added the name of Kirby. So that's the important fact from topology. Next, I'm going to relate it to our graphs, but maybe first let me pause to see if there are any questions about this. So the connection to graphs comes in the following way. So if our knot is like shown on the picture, then it's non-trivially knotted or linked. So that's actually why topology is very rich. And one of the questions, I think yesterday or the day before, was about, say, connection to something simple like Riemann surface cross S1 and so on. That's why topology in 3 dimensions is much, much richer, and in 4 dimensions is even richer than in 3D, precisely because you can have this non-trivial effects of knottedness, and fundamental group appears and plays a very important role. Or you have this braiding, in other words. This is completely new dimension, and the world of possibilities explodes. But imagine that we're doing surgery on something fairly simple. So it may consist of several components, but if these components are individually represented by unknotted circles, just like unknots. So I'm trying to draw a picture, and necessarily, I'm sure I'll mess it up. So let's imagine we have something like this. So let me try to draw more components so it becomes a little less trivial. Something like this, and add another one maybe here. So each piece here is individually unknotted. So if you remove the other components, there are just trivial embedded circles. These are called unknots. And therefore, this data of such a link with some surgery coefficients, let's call it A1, A2, now these are integer surgery coefficients, A3, A4, A5. In this case, I have 5 components. It can be represented just by combinatorial data of the graph, where to each component I associate a vertex. So for example, this would be A1, this would be A2, and if they are non-trivially linked, I'm going to draw an edge. So hopefully you see what's going on. So this would be A4 and this would be A5. So instead of drawing a link, which I was struggling with, it's much easier to draw a graph which basically encodes all the relevant data. All the data of how they are linked is encoded in this graph, and that's exactly the graph that we saw in the very beginning. So connection to graphs, and again, they may have thousands of vertices and so on and so forth, is precisely via this dictionary, and it works only if each component is intrinsically unknotted. So graph basically represents many simple pieces, but perhaps put together in an interesting way where they're linked. So this particular class of manifolds, which can be obtained by construction on this sort of graphs, is sometimes called graph manifolds, or a more proper term is plumbing construction. So these are also called plumbed 3 manifolds. And just like earlier, I gave you a Venn diagram illustrating how many different vertex algebras we may possibly have. Let me try to draw a similar Venn diagram illustrating how many different 3 manifolds we have and how they relate to each other. So first, we already saw examples of Breeze-Korn spheres. So these are some manifolds that I'll call sigma P1, P2, P3. One of my examples was precisely of this type. So these are Breeze-Korn spheres. And already this class is much richer than class of 2 manifold, because any 2 manifold is basically labeled by 2 integers, namely number of handles and number of holes, or number of punctures and the genus equivalently, whereas here we see 3 integers, P1, P2, P3. So that's already kind of a pretty big infinite family. This family sits inside a family of so-called ciphered manifolds. So that's strictly bigger. So the ciphered family, so maybe I should change color to something like this to illustrate it, sits inside a family of plumbed manifolds. That's the ones that are associated to graphs. Oops. Plumbed. And they're labeled by gamma. And this family in turn sits inside the most general 3 manifolds. And they're labeled by, if you wish, various decorated knots and links via the surgery construction, via the theorem of Licorice, Wallace, and Kirby. So this is like onion or orange, where well, onion is probably a better analogy, where there are many layers, many different structures, and if you want something simple, we can go to the core of it. If you want something more general, we can go further to out layers. In particular, we see that this plumb manifolds, which have to do with graphs that we discussed in the beginning, are fairly general, so that they include lots of classes. In particular, S1 cross-Riemann surface is already in that class. In fact, it's already in a smaller class of Seifert manifolds. But they are not everything. So there are many other 3 manifolds which are not plumbed, which cannot be connected even by Kirby moves to plumbings. Sometimes I should point out that there are manifolds that can be via Kirby moves brought from one class, kind of, they may start life as surgery on a knot, but via Kirby moves you can express them as plumbings. In that case, we put them in a class which is plumbed. So that's why it's a strict inclusion and meaningful Venn diagram. So it's an ordered set. Okay, any questions so far? So this hopefully explains connection to topology and what we were doing earlier. And that's I promised that we can call graphs 3 manifolds, and this is the reason why. But it now also calls for important ingredient, namely, how do we generalize that integral formula to more general surgeries on graphs, sorry, not on graphs, but on nodes and links. So this plumbing situation is where each individual component is unknotted, but what if it is knotted? So in other words, suppose I have a surgery on some non-trivial knot like a trefoil, as in the previous illustration. What do I have to do? Well, remember that our formula was as follows. If you had a graph, which by now we can think of as a sort of link like this, so that's equivalent presentation of the same thing, with various coefficients A1, A2, and so on. Then to this we associated an integral. So this was defined as multiple integral with a bunch of variables associated to vertices, dxi over xi. Then there was product over various terms coming from vertices and edges and so on. And suppose now I want to replace one of the components in my link by something non-trivial. So in other words, instead of this last component, I'm going to put a new one, which I'll draw in different color. And suppose it's linked with everything else like a trefoil knot. So let's see if I can draw it consistently without making a mistake. Maybe something like this. So in other words, I want to replace this piece by something which is knotted. So then what will happen is I'll have to modify part of the integrand, and luckily everything was expressed as a product. So if I make a change in one place, I'll modify it only in that one place. Dependence on this variable xi associated with this vertex I will be changed. And of course, it will depend on what here we choose for knot, or more generally a link. So we'll need an integrand that depends on Q, that depends on this integration variable, and that depends on a knot. So therefore, we need to construct this object or this part of the integrand. And if I tell you how to do it, then we're basically done. For topology purposes, we can compute these things now for completely general manifolds. So basically, what's going to happen today is, from topology perspective, generalization of first lecture to completely arbitrary knots and links. So let me explain how to do that. So for this, we need quantum groups. And that's why I was saving this part for later, because in the first lecture, I showed how to define everything using basic integrals and rules of calculus, whereas now quantum groups, of course, is a slightly more advanced subject. So let me start with the usual definition and constructions. So UQ of SL2. So as said before, we'll do everything just for Cartan type A1, SL2. So this will be usual quantum group which is associative algebra. Here we go. So associative algebra over the field which is fractions of Q, C of Q, with the usual generators which are Chevalier generators, E, F, and K. For SL2, there is only one of each. E, F, K, and K inverse. And they obey the usual relations, which are K conjugating E is Q square E. Sometimes people use square root of Q instead of Q, and so on. K conjugating F is Q minus 2F. And most interesting relation is the commutator of E and F, which is K minus K inverse, Q minus Q inverse. So it's a Fern algebraic structure. Okay. What's going to be important for us are representations of the quantum group. So representations. Most familiar are finite dimensional representations, say representation of dimension n let me denote it Vn. As usual, can be decomposed into sum of weight spaces or K types. So Vn of J, such that it starts with a lowest weight space, Vn, where J is 1 minus n. Then E and F act as raising and lowering operators, taking us from one weight space to another. So E is like raising operator, F is a lowering operator, and they change J in steps of 2. So in the end, for n-dimensional representation, we end up at the last step with, so let me shift it so you can see everything. We end up with Vn, where this index J is equal to n minus 1. And dimension of this, or rather quantum dimension of this n-dimensional representation is basically Q to the J dimension of Vj, and in this case, it comes out to be the quantum n, which is Q to the n minus Q to the minus n, divided by Q minus Q inverse. So this is very similar to representation theory of usual SL2, not quantum, which in fact can be recovered by taking Q to be 1. So I'm assuming that many of these things are familiar. Indeed, they're very, very parallel to standard representation theory of SL2, but part of the reason I'm summarizing this here is to be self consistent and self-contained, but also to establish the notations that we'll use in a second for something more interesting. So something more interesting has to do with infinite dimensional representations. So that's the next bullet point. So infinite dimensional highest or lowest weight Verma modules. So first of all, so let me denote them by their dimension. So they're V infinity in our notations, or notations similar to the above. So there also can be highest weight or lowest weight. So let the upper label represent that fact, whether it's highest or lowest weight. But most importantly, they're labeled now by non-integer highest or lowest weight, which I'll call lambda. An important point is that this lambda is now a general complex number. So this is, of course, not surprising, and again, very similar to what happens to, say, representations of SL2C, highest or lowest weight representations of a classical group. And in terms of that structure of weight spaces, it's very similar. For example, for highest weight, the corresponding diagram will look like this. It will be V infinity of lambda minus 2, then eventually going to V infinity of lambda, the highest weight space via this action of E's and F's. And previously, we had some variables xi associated to, which were integration variables in these graphs and various other places. So I can already make contact with those variables by saying that let's define x to be q to the lambda. So it basically is exponentiated highest weight, which again, just like lambda itself, is now a general complex number. So that's, we're slowly making connection to notations of the above. Similarly, one can define lowest weight Fermat modules, as well as their extensions, which will be principal series representations of quantum group. Again, important point is that they're all infinite dimensional, and their weights are complex numbers. So this is something that has not been used as much in quantum topology in the past. For example, many of the quantum invariants that you may have heard about of Arishetikhin, Turaev, and others are related to quantum groups, first of all, at roots of unity, and secondly, and more importantly, to finite dimensional representations. Whereas here, we're not going to do either one. So we're not going to assume that Q is a root of unity necessarily, and more importantly, we'll work with this infinite dimensional Verma modules labeled by complex weights. So for completeness, and if you didn't have much experience with quantum groups so far, let me describe how ENF acts specifically on the basis vectors. So I'll introduce basis vectors Vn with n being non-negative, such that Vn lives in the space lambda minus 2n, again, just for highest weight Verma module for simplicity. And then E acting on Vn will, let's let's see, take me to lower value, so it will be n v n minus 1. F acting on Vn will produce analogous Q number of lambda minus n, Vn plus 1, so they're changing these labels accordingly. And K does not change n, but produces an eigenvalue of Q to the lambda minus 2n. And this basically completes the description of these reps. So now, important point is that there is an R matrix associated with these representations. In fact, there are two R matrices. So R is an R matrix which is an operator acting on two copies of V infinity of say highest weight or lowest weight Fermat modules with certain complex weights. So usually R matrix is represented by a diagram which looks like this, since it acts from V tensor V to V tensor V, but it carries a bunch of labels. So these two strands may represent the Fermat modules of different complex weight, and we introduced already either lambdas or their exponentiated versions x and y. So this could be labels here. In addition, there are basis factors in each of the modules, which we label by either j or this little n, and correspondingly, you also have this diagram decorated by this data. Let's say I, J, K, and L. So I, J, K, L are all non-negative integers with our conventions, and X and Y are complex numbers. So as a result, this R matrix depends on a bunch of numbers. It depends on Q, of course, which again is assumed to be generic, not a root of unity. It depends on two complex numbers, X and Y, which have to do with highest weight and our general complex number. And they depend on integers, I, J, K, L, which represent the states within the corresponding module. So R matrix is again map from V tensor V to V tensor V. Those of you who are familiar with integrable systems should not confuse x's and y's with spectral parameters. They have nothing to do with each other. This is different data. Similarly, there is inverse R matrix, which we can graphically represent in a similar way. So this will be analogous diagram, but with represented by a different type of crossing. So again, decorations are such that the strands carry complex weights, x and y. In addition, there are these discrete labels I, J, K, and L. And yeah, everything also depends on Q, of course. So any questions so far on this? So this is a review of quantum group, its Fermat modules, and corresponding R matrices. So then we can use, so we got pretty much everything we need. So next statement is due to Sang-Yuk Park. So his recent work from 2020 and 2021. So during the COVID time, which basically says the following, that for a knot or a link K, represented by some diagram like a trefoil knot. So let me try to draw this one more time. We can basically retrace the knot, so give it orientation, and retrace the knot such that every time we see a particular type of crossing, we associate to it an R matrix or its inverse. And if we label everything by this complex weight X and use this universal R matrices associated with Verma modules, we can basically define an object, which I'm going to call f k of x and q, because it depends on choice of x, and that's the complex weight of Verma modules. It depends on q, which again we assume to be generic. So this is viewed as invariant of a three-manifold that has a torus boundary. This is something that came up in questions last time, and basically can be defined as a trace, namely sum over all these labels I, j, k, l, and so on and so forth, of a product of R matrices associated with, and their inverses associated with different crossings. So at each particular crossing, we put our friend Rijkl, which depends on, in this case, x and x. So the complex weights are the same. And of course, it depends on q, which again is assumed to be generic. Similarly, if you have a link with several components, what's happening is that you'll have now, there are two different components. They don't necessarily talk to each other, and therefore there is no reason why x1 has to be equal to x2. And that's how you get multiple integration variables in the surgery formula or integral formula that I showed you in the very beginning. So as a result, this gives a definition of integrand that you can use to construct such invariants for general three manifolds. Again, this is important for applications to topology, but for connections to VOAs, this is already in some sense overkill, because even with these graphs where everything was at the undergraduate level of mathematics, one can make everything computable, well-defined, and already ask lots of questions there. Namely, for example, you guys already asked questions like, how do we promote this to operations on vertex algebras or vector spaces? And these are precisely good questions. That's where I would start. But topologists, they want general knots and three manifolds, and therefore this construction is in some sense important in view of this theorem of Licorice-Wallace and so on.
Can I ask a quick question?
Yeah.
So to define this trace, so you mentioned a trace, right? So I suppose you need unit and co-unit maps. Are they similar to in the case of finite dimensional representation, similar formulas? Or?
Yes, they're essentially conceptually the same, I'm tempted to say, but there are various things that need to be done very carefully, because now when we're tracing, we're summing over infinitely many values of I, j, k, these labels. Right. So one has to be super careful, and I don't plan to go in details, but Sang-Yuk Park invents several good tricks which prefer, for example, if you have positive crossings in a knot, you should use highest weights. If you have negative crossings, you should use lowest weights, and so on. So he explains how to do. I mean, there are very important, delicate features which I'm sweeping under the rug, but they'll come in. But other than that, it is what you expect it to be. So I would say that in some sense, these details are most interesting part of his work, but conceptually it is very similar to analogous construction of, say, John's polynomial that one can use using finite dimensional representations.
Okay, thanks.
Yeah, that's a good question. Right, I want to make a remark since I already did all the work introducing this quantum group. Let me make a comment. So here I used generic values of Q, but one can imagine taking Q to be a root of unity starting from here. So we had our UQ of SL2. Again, many things you can repeat for general SLN or even other Cartan types. So I leave this as work for those of you who are interested. But let's just start with the same SL2. And in the Q plane, try to take a limit where Q, which was assumed to be generic, let's say inside the unit disk, goes to root of unity. And I'll take it to be even root of unity, pi I over P. So 2pth root of unity where P is even. Right. In this case, so why this is interesting and important or relevant for us? So remember, one of the various relations in the definition of quantum group had the form, for instance, where K conjugating E, for instance, the Chevalier generator was Q squared E, right? So if Q is root of unity of some even order 2p, then repeating this operation p number of times will give me identity on the right-hand side. And in particular, you can see that at this root of unity, at 2pth root of unity, our definition or commutation relations of the quantum group were consistent with additional relations where we can assume that K acts in a unipotent way. So K repeated 2p times will be identity, and also e to the power p as well as f to the power p are zero. So in other words, E and F become nilpotent. So what this defines is this particular truncation of this quantum group, if you wish, a generic Q, is what's often called small or restricted quantum group at the root of unity. It's denoted by UQ bar. That's the usual notation for the restricted form. And what's nice about it is that, first of all, it's now a finite dimensional thing. So dimension of UQ bar, it depends on choice of root of unity, which for us was parameterized by p, and in this case is 2p cubed. And also, it has a finite dimensional center, which the fact that it's finite dimensional is not surprising, since the whole thing is finite dimensional, and dimension of the center you can also work out. It's going to be 3p minus 1. But what's interesting is that the center carries a lot of cool structure. So in fact, now you can, there are several passages to logarithmic vertex algebras which we already encountered, and I'll briefly mention just one of them, but there are many others. For instance, you can try to study the category of representations of either this quantum group or its close cousins. So depending whether we include square root of k or not, it will have slightly different structure, namely will be triangulated or not triangulated. Or you can just look at the center and ask what the center looks like. So interesting thing is that it carries several decompositions. In particular, it carries an action of SL to Z modular group. and decomposes into SL2Z reps. So let me maybe write it down. So you can write this Z as P plus one dimensional representation of SL2Z plus two-dimensional representation of SL2Z, which I'll denote by C2, tensored with another representation of SL2Z, which appears in the context of non-logarithmic or rational VOA, namely WZW model. And this is the familiar Verlinde representation, so I'll call it accordingly, Verlinde of dimension P minus 1. So this whole package, now with WPs included, is precisely the same as 3P minus 1 dimensional representation of SL2Z that I mentioned earlier in the context of discussion of triplet algebra. So when we were discussing various logarithmic vertex algebras, I mentioned that several facts about triplet and singlet, and in particular, there was a number 3P minus 1 appearing there, and this is the same 3P minus 1. So this is not terribly relevant for our discussion today, but since we already had all the ingredients on the whiteboard, I want to mention this in passing. And also, maybe let me mention that sometimes one uses analogous decomposition of this center of the small or restricted quantum group. Again, there are many different variants, and they're all cool, very interesting, and one can look at different roots of unity, even versus odd, story are closely related but slightly different. And another decomposition that you may often see in the literature is decomposition into blocks. So in the case of center for SL2, I mean for this restricted group of SL2, it will look a bit differently. So it will consist of pieces of different dimension. So there will be three-dimensional piece repeated some number of times. So this is so-called three-dimensional block or regular block because it's the same as dimension of the SL2 itself. And it occurs P minus 1 times. Plus, there is a one-dimensional block, which occurs twice. This is often called Steinberg. And this sort of decomposition is something that you can encounter in recent works of, say, Roma Bezrukovnikov or Anna Lashovska and various others, where in some sense it's a cutting-edge discussion and story where analogous formulae for other carton types in various other characteristics are not even known at present or until recently, not to mention the structure of the SL2Z action. So part of the reason I'm mentioning this is for us, if we're interested in applications or relations to vertex algebras, it would be interesting to understand how SL2Z acts, say, for other carton types in higher rank. And as far as I know, this is not known. So this is another good problem to work on, but this is a non-trivial serious problem. And hopefully these connections that I'm mentioning to various other subjects will be helpful or may shed light on even these deeper questions. So this was a remark in passing. Any questions about this before I move on? Okay. So then
we have a question.
Maybe what? Yeah.
Okay, excuse me. Just to be sure I'm following, so you have defined two invariants, one for plumb manifold which are closed, another for not exterior, links exterior. And did you mention any relation between these two?
Yeah. So right. They're basically, the point is that they're the same. So let me try to clarify this. Thank you for the question. So this general theorem of Licorice-Wallace and Kirby, which includes the equivalences, says that any three-manifold can be constructed out of surgery on a link in a three-sphere. So this is a big three-sphere. Oh, sorry, let me move the board. So imagine that you have some link sitting inside, something that looks like this, with various components and so on. And I mean, there may be non-trivially noted amongst themselves and so on. So the point is that you can remove the neighborhood of this link and reglue it back and produce any general three-manifold. So that's hopefully that's clear. Now, this link is labeled by coefficients, the surgery coefficients that tell us how exactly we're going to reglue back each component. And they're integers, A1, A2, A3, and so on. So when this link is consists only of unknotted circles, so in other words, when you don't have non-trivial knotedness itself on each component itself, you can say that, aha, I represent the same data. So now with the surgery, it's a particular three-manifold. So that's statement of theorem of Licorice and Wallace. But you can represent exactly the same data, but just by telling me how many components you had and how they're linked together. So for instance, in this illustration on the left, I guess we're going to get a graph which looks like this. It has these decorations A1, A2, A3, and so on and so forth. And it's supposed to mean exactly the same thing.
Yes, but on the other invariants, they're defined for links exterior, so they are not closed manifolds. They are.
Oh yes, that's right. So good. Yeah. So then suppose if you have something more non-trivially knotted, for instance, if K is again, unfortunately, the only knot I know how to draw is the trefoil. Something like this. It's not unknotted. It's non-trivially knotted. Then what I showed you is how to construct, using this work of Park and Verma modules, Fk a function of x and q, which then you take and stick into the same integral that we had before. So the rest of the definition for closed manifold is the same. So z hat of a surgery, namely this three manifold, which is some surgery on a knot with some coefficient. So that's the three manifold, is defined in the same way. So it's still integral dx over x on a unit circle, and the only part that changes is basically so theta function remains the same. And the only part that changes is the integrand. And what I told you is how to get the integrand. So now if you have general knot or link and know how to compute the integrand, you basically do the same procedure. And same as we had in the first lecture.
There was some homology class like spin charge structure.
That's yes, that's exactly right. So yeah.
Side?
So spin C structure came from choice of surgery coefficient, and it was a label that came essentially from theta function. It came as a characteristic, and indeed, so there will be this additional label B. It will, in general, for say, 3-manifold, which is some surgery over naught. So in this case, M3. What is this? This is H1 of surgery, which is, let's say, P over R surgery on some knot K. This group is always ZP. And that's a topological fact coming from surgery, but this theta function will know it automatically. In other words, if it use the same theta function as before, then with this A's representing, say, P over R, it will automatically give us as many labels as cardinality of ZP. So this ZP is, in my conventions, it's basically Z mod PZ. So it has cardinality P. So indeed, there are P labels. For simplicity, if you wish, we don't need to worry about it. So everything that's in red in this lower expression and this labels B, we can ignore because there are additional decorations. But yeah, you're absolutely right that they're there, and this part is exactly the same. So that part is unchanged.
Okay, thanks.
Yeah. So, but again, if this surgery stuff is too topological, feel free to ignore it. We can go back to this graph manifolds, and even there is a lot of fun to be had. However, maybe last thing I want to explain in this lectures. Oh, actually, I missed one thing, which maybe will be helpful for this question. So let me make another remark that the surgery can be thought of as in a different way. So yeah, so another remark. So what I was explaining a moment ago is that indeed you can think, at least in some cases, of this diagrams of knots and links as graphs, but the diagram itself is what's called Kirby diagram. So this picture that we had with various knots and so on, with label decorated by A1, A2, this has a name. This is called Kirby diagram. And it defines two things at once. So first of all, it defines a 3-manifold via this surgery technique that I explained above. But I want to make a quick comment that it also defines a 4-manifold with boundary. So in topology, one can start with this diagram and picture the following. So imagine that we start with a 4-ball, which is basically 4-dimensional disk or ball, and it looks like this. That's the cartoon for it. So now it's a solid ball, and it has 3 spheres as a boundary, right? So you can imagine adding to it so-called 2 handles, which are copies of D2 cross D2 attached along. So on the boundary of this 4-ball, we can draw a diagram over knot or link, very much as before, and we can attach to the neighborhood of this diagram. So I'm running out of dimensions, so let me maybe place it like this. A new object, which is going to be this red thing, and it's a copy of D2 cross D2, but it may be attached in a non-trivial way to a knot in the boundary. And then the resulting boundary of a new thing will be a new 4-manifold, which will have our surgery on a knot as a boundary. So this blue thing, light blue, will be precisely the result of surgery on K with some coefficient. So there is another way to think about this construction, and this is basically beginning of Kirby calculus, and that's why this is called Kirby diagram, and the corresponding moves are called Kirby moves. So I didn't want to go too far into it because proper discussion will be the whole one-year course on Kirby calculus. It's very beautiful, very interesting. But the reason I want to mention it is to emphasize that the same data actually defines a four-manifold with boundary. And this boundary is precisely this surgery of a three-manifold that we discussed before. I didn't go in this lectures into exploration of vertex algebras associated to four manifolds, which, as I mentioned, is even more tricky, more interesting than for the case of three manifolds. But I want to point out that you can use similar techniques, and richness is at least as vast as what we're seeing here. So for introductory lectures, I think it's a good idea not to go too far that direction. But I want to point out that it's a natural continuation, because the same diagrams define both three manifolds and four manifolds together. Right. Okay. Anyway, last thing I wanted to note is to come back to this question: what kind of function is this object? So. For a closed three-manifold that's, let's say, obtained by some surgery on some knot K, this, or more generally link, this is obtained by performing this integral over the integrand, which depends on this knot of x and q. So that was defined using quantum groups at generic Q and corresponding Verma modules. So there is a convolution with a theta function. And the question was, what kind of object is this? Namely, as a Q series, is it a Q hypergeometric function, and or what else? So it turns out that, and a priori, I wouldn't know how to answer this. Like I said in the beginning, for a general graph, it's quite non-trivial. And it seems that making things story about knots and links will only make it more complicated, but this is not quite true. So recently, there was a lot of work on so-called knot quiver correspondence, which answers precisely this question for the integrand. And the integral inherits this property. So these recent developments tell us that this object, the integrand that we were discussing using quantum groups and Verma modules, has a very particular form. So this fk of x and q has the following form. So I'm going to focus on this part of the formula now. It can be written as a multisum over integers, di, which are non-negative integers, all of them. There could be some number of these guys. Then it will be of the form which is very similar to theta function, and will involve q to some quadratic power in these summation variables, times x into to the linear power. So there will be product over I x to the di. Then numerator of this will involve q to something quadratic. So let me call it q to the half d dot c d, where hopefully the notations are reasonably clear, that C is supposed to be some matrix of the size, depending on how many D's, summation variables we have, plus something linear. That's not terribly important. And denominator is of the form q to the d, meaning that this is basically product of Kuppenheimer symbols. So this is shorthand notation for product over I, QQDI. Okay. Now, why is this interesting? So the statement is that for each node k, there is such an expression. So on the one hand, it comes from so-called node quiver correspondence. And it's called knot, well, because there was a knot. For every knot, there is such a form. And quiver, because this metric C that runs the show, notice that in this formula, the crucial ingredient is this matrix, which appears as a quadratic form in the numerator. Suppose it has a form, for instance, something like 0, 1, 1, 1, 2, 2, 3. Okay, then to this matrix can be viewed as adjacency matrix of a quiver, which has 3 vertices. So quiver is a set of vertices and arrows. So in this case, there will be 3 vertices, and the story is very similar to what we did with graphs before. Now, the only difference is that each time we see something on a diagonal, we'll interpret this as arrows going from vertex to itself. For example, first vertex had no arrows going to itself. On the other ones, we have 2 and 3 on the diagonal, so I'll draw corresponding 2 and 3 loops starting and ending on the same vertex. Now, the off-diagonal values are exactly the same as what we did with graphs in the first lecture. They express connectivity, except, again, that they're just oriented. That's the only difference. For example, first one is connected to the other 2 via 2 arrows going back and forth. That's the off-diagonal ones in the first row or column in this matrix. And vertices 2 and 3 are connected by a total of 4 arrows, 2 of which are going one way and 2 of which are going the other way. So this knot quiver correspondence relates data of knots to combinatorial data of such quivers. An important point is this connectivity matrix, which becomes the matrix C in the formula I showed. So why would it help to anyone? Well, those of you who are old enough, like me or Terry, for instance, would quickly recognize that this form here, this form that I'm going to put in a box for FK, I'll put it in yellow box. It's actually something very special. This is something that came from early 80s when people were studying the connections between vertex algebras and integrable lattice models and R metrics. So this was beautiful time when all these connections were just about to be developed. And in those days, if you look at character formulas, you often see expressions written precisely in this form. So this form has a name, which goes back to early 80s, and this is called fermionic form of a VOA character. Fermionic form of VOA character. So in other words, it's a form for some character chi which depends on q, and in this case on the variable x, which is written in a fairly universal form where denominator is completely universal. It's basically product of Kuchba-Heimers. And the numerator is essentially like a theta function, and the most important ingredient is this metric c. So in the lattice integrable models and corresponding VOAs, this matrix plays a very important role. It's the star of the show. And that's exactly what this not quiver correspondence gives you. So in other words, now if you know how to represent your three-manifold, not as terms of graph, as originally we did in the first lecture, but as a surgery on some knot or a link, you can actually write this result in a closed form, so you don't have to guess what the answer is. I showed you how to compute it to, say, 500 terms in the Q expansion, and then, of course, one can try to stare at it and see what the modular properties are, and so on and so forth. But you can actually now just use this fermionic form. It's very easy to do the integral. It's clear. It's easy to see that it's not going to affect the general structure. So even if you do this integration of a variable x, the answer is going to be in that same form, namely this fermionic form. Okay. So in particular, for instance, if I go back to, I'll just give you one example, which was this original example with which it all started, namely the case of simple Breeze-Korn spheres, like let's take three-manifold to be that same example I illustrated in Mathematica, namely the Breeze-Korn sphere is sigma 237. That's for us, it was given as a very simple graph, but actually that same manifold can be obtained in a number of different ways. So first of all, you can obtain it as negative surgery on a trefoil knot. This knot 3-1. That's the only one that I say I know how to draw. That's this guy. Or it actually can be obtained as a different surgery on a figure-8 knot. And this gives you, first of all, opportunity to verify that everything is invariant under Kirby calculus, so that same manifold constructed in different ways produces the same invariant. But if you now use this presentation, not in terms of the graph, but rather surgery on these other knots and not quiver correspondence, you can produce the expression for this object z hat of Q, which previously we had to guess what it is. And if we want to compare it to some character of log VOA, we had to do non-trivial work. But now it's already given to us in the form of in this fermionic form from 80s. So I'll give you a closed form. It's in this case one-dimensional sum, and you can write it as sum over, let's say n going from 0 to infinity, and explicit expression is this one. So it's q to something quadratic divided by Kuchba-Heimer. So quadratic thing is going to be 1/2 n times n plus 1. So it's you can think of C as 1-by-1 matrix. It's one of the easiest things. Q to the n plus 1 Q and Heimer. This is not actually how it comes out from this trefoil knot or figure-8 knot, fermionic forms using the quiver correspondence. In those cases, you would get a matrix which is of size 3x3 or 4x4. So I here did something to massage it. But in any case, this is now a closed form expression. And I just want to illustrate that similar things you can do for many other nodes. One thing I want to point out is that this now opens the door for exploration. And it's actually quite surprising that these fermionic forms of characters that were popular in 80s and early 90s suddenly show up in this business of knot-quiver correspondence. Neither of the subjects is something that I personally worked on, so I have absolutely no stake in it. And to me, this was an interesting surprise, why this happened to be breached by this development. So I think this is something for all of us to explore further. But I want to point out one interesting thing that is the following. So also in the beginning, I assumed that matrix Q, which was basically the surgery matrix, is negative definite. So let me ask, what changes if we make it positive definite? In the corresponding manifold, that means that we reverse orientation. So instead of M, in this example, for instance, we can consider minus the manifold. That's the manifold with opposite orientation. So what this means is that now if I represent it as a surgery, I'll have +1 surgery on a trefoil and -1 surgery on figure 8. So again, the surgery formula for general knots will help us how to compute things. So we can do it either using this technique, and then quantum groups a generic Q and our matrices for Verma modules, and then just apply the surgery formula. And what we'll find is the following. So now if we compute the result for z hat of -M3, the result will be the following. It will be Q to the -12, sum over n from 0 to infinity. Again, it will be written in this fermionic form of VOA character, Q n plus 1 Q n. But something nice now happens. If you stare at this formulae for manifold with one orientation and the other, you may notice something. So in other words, if you take the top formula for manifold M3 and replace Q by Q inverse, you get the other formula. So in other words, in every term in the summation, you can do the following thing. Take Q and replace it by 1 over Q. Of course, what you'll get is some, again, ratio, which will be ratio of Q inverse polynomials, but multiplied by some big overall power so that everything, again, is written in terms of Q. And what you're going to get is exactly the other formula. So what this teaches us is actually a general principle that for manifold and its reverse orientation, these two functions are related by analytic continuation across the real line on a tau plane. Or in Q variable, if you go from inside of unit disk to outside of unit disk. So therefore, the picture is that in a tau plane, so I'll draw it next to these expressions. We have something, we have z hat of, say, manifold M3 and as a function of Q. And if we try to go through this boundary of a natural domain where the function is defined into lower half plane, then we're going to obtain precisely z hat of -M3. From topology point of view, this is natural operation, and you can justify it in many different ways. It's actually not surprising. You would expect this property a priori. But from the viewpoint of relation to characters, it teaches us something interesting, something I don't know in general. If this is meant to be, if each of these guys is meant to be a character of some log VOA, then it suggests that there should be a relation, like a mirror symmetry, between two different log VOAs, such that their characters are related by this exchange of Q and Q inverse, where Q inverse is in quotes, it's meant to be rewritten in terms of Q, or by this analytic continuation. So this reminds me of positive and negative zone in the Kazhdan-Lustig correspondence. Again, I don't know deeper meaning of this operation from the viewpoint of log VOAs, so I guess I leave it as an open question, and will be happy to hear any thoughts or suggestions that any of you may have. It basically points out that there is some mysterious duality between logarithmic vertex algebras, which has the meaning of kind of analytically continuing from upper half plane to lower half plane in terms of tau. Roughly speaking, it should probably correspond to changing level to minus the level. Again, I don't know what it is, so I think I better stop and perhaps answer simpler questions if you have any.
Questions or comments? Maybe in Zoom?
I guess I have a naive question. Are there any cases in which this VOA invariant is expected to be rational?
Rational in the sense of rationality of vertex algebra, right?
Yeah, rational CFT or rational VOA.
Yeah, so the first homework that I suggested, where you take single vertex and so I can put it here as a side comment. So manifold obtained by surgery on a single unknowed component labeled by P is a length space. It's LP1. That's one simple graph or three manifold if you wish. And in this case, you basically get rational characters of rational VOE. You basically get usual Fock modules of something like free boson. I don't know other examples. I wouldn't be surprised if there are some, but I didn't encounter any.
Okay.
It seems like for some reason that this story wants to be logarithmic, and I don't know why.
Well, I was going to comment that if the knot gives you this fermionic character formula for the VOA, then if the VOA is rational, then you know that its character is a modular form, and then asymptotic behavior puts some very strong condition on the matrix that appears in this fermionic formula. So, yeah, I was going to ask if you know if there's some corresponding condition on the knot, perhaps that.
Yeah, that's a good question. As far as I know, all these matrices C, so they can be computed for or have been studied for various knots. I don't think they satisfy this Bloch group or K-theory condition that correspond to rationality in VOA terms. Yeah, so that's probably part of the reason why one should expect that rationality is extremely rare. Yeah.
Right.
Generic things probably are non-rational in the sense. Yeah.
Okay, thanks.
Any more questions? Okay, so let's thank Professor Gukov again.
Well, thank you all for attending, and if you have more questions, feel free to email me at any time.
Thank you.
Thanks.
Very interesting lectures.